So today we'll be doing some calculation questions for our quiz, which is in at 7-8 hours. So we have springs for helical compression expansion springs. So let's focus on example 23.1. So we're given the following information. We're given mean diameter of the coil, which is our capital D, which is 15 millimeters. We're also given small d, which is the wire diameter of 5 millimeters. We're also given capital N for the active number of coils, 20. And we're given if the spring is subjected to an axial load of 500 newtons, so our F is 500 newtons. Now, calculate the maximum shear to which the spring is subjected to. So that's what we are asked to do. We're given this information. This is part of the formula sheet that will be given to us. I think one of the friends passed it down to me. So how do you do this? Very, very straightforward. All we have to do is just sub into this formula. Now, you can use any of these formulas. You can use it in here. You can use it in here. But it's very simple just to do here. So you can just use it here. All we have to do is find out what C is. So our C, so maybe I'll do it in a different color. So C is capital D over D. So we have 50 over 5. This gives us 10. Then our tau max, which is our max shear stress, will be 8F over pi D squared C plus a half. Now this will be equal to 8 times our force, which is 500 newtons, over pi, and our small d will be 5 squared. C plus a half, C is 10, 10 plus a half. Now let's check this in our calculator. So we have 8 times 500 over shift pi multiplied by 5 squared, and then 10 plus a half. So this should give us, this gives us tau max in, this is, if you notice, this is in meters, and this is Newton per meter squared will give us pascals. So this is answer will be in pascals. So we have 534.7 pascals. For 7.6, let's round it to 0.8. All right, so this is example 1. Now, this won't be Pascal, this will be in megapascals. Sorry about that. So this will be in megapascals. Forgot. MPa. So this is our final answer. Now, let's go on and try another question. So this question was given to us in the tutorial. So if you look over here, so if we go down over here and just place it here. So we're given a helical spring. Helical spring is made of a wire of 6 millimeter diameter. So again, this is our small d, 6 millimeters. And it has an outside diameter of 75 millimeters. So outside diameter means capital D, O, 75 millimeters. Now, if the permissible shear stress is 350 megapascals, so tau is 350 megapascals, and the modulus of rigidity, which is our G is 84 kilonewtons per millimeter. So 84 kilonewtons per millimeter, which is pascals. But we're just going to keep it as it is, millimeters squared. Find the axial load, so our force, which the spring can carry, and the deflection per active turn. So deflection, they're saying deflection per active turn. So this is what they're asking about. So having said that, let's look at what we can find out. We know that the mean diameter, capital D, is our outside diameter, take away the small diameter, right? So this will give us 75, take away 6. This will give us 69 millimeters. Now, with this, we have D, we have small d. We can work out capital C. The capital C, our spring index, is big D over small d. So 69 over 6, right? And let's check what this will give us. So 69 divided by 6. This gives us 11.5. So we have C as 11.5. Now, next things, we found out what C is. Now, to work out the deflection per active turn, look, we have a spring constant K over here. We also know that F equals K del X, where del X is our extension we're trying to find out, right? This is our our extension, we can rewrite this equation as F, or axial load, which we're trying to find out, right? We're trying to find out. And so if I was to just rewrite this over here, so before we do anything, we have to work out Ks because we will need it in all of our calculations. If you look here, to find, because we're given T max, we can use this to find out the force, because we have T max is our 350 megapascals, we have F, we have capital D, we have small d, and so we can find our Ks, so we can find our F from here, right? And we also know C as well. So we can use this formula to work out our axial load. From the axial load, we can work out our deflection per turn. Now, let's try to find it out. So Ks is 1 plus 1 over 2c, right? So this is 1 plus 1 over 2 times 11.5. So let's check this. Or alternatively, we can just use this formula. So if you want, let's go with this approach. Maybe makes more sense. So tau max equals 8f over pi d squared c plus a half, right? So let's put in these values. So we have 350 times 8f, which we don't know, times c plus a half. C is 11.5 plus 0.5. all over pi, and our small d is 6, so 6 squared, right? So what we can do is we can rearrange for f. So if I was to rearrange, this would be 350 pi 6 squared over 8, and 11.5 plus 0.5 is 12, and this will give me f. So now let's check if this f is what we need. Let's check. So 350 times shift pi, shift pi times 6 squared over 8 times 12. And this gives us 412.33, which is what we wanted as well. Now, Ks, yeah, f pi d squared, f pi d is 6, yeah, f, yeah. Yeah, that should be fine. Okay. All right, so 412. So we can just write it as 412 newtons. This is the force we're going to use. Now, if you look over here, we have F equals kx. So if we were to rewrite this, right? So if we can rewrite this, this would be. So if I add another page, hold on. I think. Oh, there we go. Add page. Yeah. So now to work out so we're given this. So if I just copy this all the way down here, so Control V, and this. There we go. So to F equals K del X, so we want delta X. So delta X will be F over K. So F over K would be F over all this. So dg over 8c cubed n. So this is the same thing as saying del x is equal to f, or 8f c cubed n over dg, right? So this is the same thing as saying, so del x would be, we want del x over n is equal to obviously 1 per active turn. So it would be 8fc cubed over dg. So 8 times our force, which we found out 412, times c cubed, which is, I believe, 6, what's our c again? It was 11.5. 11.5 cubed over small d, which is 6, and our g is 84 kilopascal, 84 kilopascal, kilonewton meters, newton per millimeter squared. So this would be 84, and we times by 10 to the power 3. Let's check. So let's check 8 times 412 and 11.5 cubed over 6 times 84 times 10 times 10 to the power 3. This gives us 9.95 millimeters, our deflection per active turn. So that's done. Now let's go on to another question. So we're given another. This was the other tutorial question where we're given design a question. So this was what we were given. To design a spring for a balance to measure 0 to 1,000 newtons over a scale length of 80 millimeters. And what we need to do is it's included in a casing of 25 millimeter diameter. The approximate number of turns is 30, so n equals 30. G equals 85 kilonewtons, kilonewtons per millimeter squared, and calculate the tau max. So calculate tau max. Tau max. Okay. So when they ask about design, you need to give all of its specifications. So the way this works here is, so we have the force. Let's take it as 1,000 here, so 1,000 newtons here. Then we know our scale length, or when they talk about length, the only length we have is the del x. So our deflection is 80 millimeters. So this is our given information, and we know that when they're saying it's enclosed in a casing of 25 millimeter diameter, what they're saying is that it has to be less than 25 meters. So our outer diameter, which is d plus small d, has to be less than 25 millimeters. Okay, now with that out of the way, let's see if we can try to see if we can solve this question. Now, previously, if you remember, we just solved for f equals kx over here, right? I'm just gonna keep the same. Gonna bring it down here because we're going to need it. So again, we have. I'll use black slate. We have f equals kx, k del x. Now, in this case, we have everything. Now we need to find what? We need to find a couple things. We need to find a couple things. We need to find c from this. Look, we can find c from this. Because we also know, do we know anything else? We're given, what else are we given? Are we given capital D? We're not given capital D. All right, we're not given capital D. So we can find out capital D in terms of c. Now, okay. So f equals kx, and we want to work out what c is. So let's say f is 1,000. Our k term is, let's say, let's give it this k term. So it will be dg over 8c cubed n, and it's obviously multiplied by our del x. Now, we know all these terms except c. So let's see if we can rewrite all this equation. So this, if we rewrite all this, so before we do this rewriting, so what if we just write f equals dg delta 8c cubed over n. We want c cubed over d, so c cubed over d would give us. So if you were bringing this to the top, so this would look like 8c cubed n f equals dg delta. And we want c cubed over d, so c cubed over d here would be, I mean, it's the same thing I'm writing over here. So that will be g deflection over 8f n. So this is what we need to calculate. So c cubed over d is equal to GA is our 85 times 1,000. Then we have our del x. Our del x is 80 millimeters. So our del x is 80. Then it's over 8. 8 and force is 1,000. So if we assume 1,000 here. And then we have our number of turns, which is 30. Right? So let's check what this would give us. So we have 85 times 1,000. Let's check 85 times 1,000 times 80 over 8 times over 8 times 1,000 times 30. This gives us 85 over 3. Now this is c cubed over d is equal to 28.33. It keeps on going. Now from this, if you remember, we had to assume a length for d. And from what we can assume any number provided it's provided our do of our capital D plus d does not exceed 25. If you remember that a small diameter was less than 5. So anything less than 5 should give us this as well. So let's try this. So if we assume that d equals 4 millimeters, what happens? We have that c cubed, right, equals 85 over 3 times 4. And then we find c. c is cube root of all this. So 85 over 3 times 4. So this will give us cube root 85 over 3 times 4. And this is around 44.839. Now, if you remember, our spring index C is capital D over small d. So our capital D would be C times D. So D would be C times, C is 4.839 multiplied by 4. Now, for storing purposes, I'm just going to store this in A because it's easier for me. So now when I go alpha A times 4, we have what we wanted. So this is 19.4, or rather, let's say 19.36 millimeters. Now, if we add DO, that will be D plus D, 19.36 plus 4 millimeters. This is 23.36, which is less than 25, so that's good. So now we need to find the maximum shear stress induced, so we need to find the tau max. Now, once we know everything, all we have to do is just substitute into this formula over here. Very simple, very straightforward. So we can just do that. So 8f over pi d squared c plus a half. 8, and we're assuming the force is 1,000. That's the maximum force. So pi small d is 4 squared. C we worked out is 4.839 plus a half. Okay, so in this case, obviously this is my A. If you want to double check, this is my A. So we have 8 times 1,000 over pi times 4 squared, 4.839 plus a half, and this gives us 849.728. So 849.73 megapascals. Right, so MPa. Now, this is assuming that we are. Hold on, not this. We're assuming that we're using KS for our case. This is over here, because it's not given. I asked the professor. If it's not given, we assume we use KS. But if, let's say, they ask about using the other factors, All we have to do is just plug in these numbers. So for kW, that is 4c minus 1, 4c minus 4 plus 0.615 over c. You just have to plug in what c is, and that's our kW. So instead of ks, you'll have kW, or you'll have kb. He will specify it. He said that if he doesn't specify it, you have to assume ks. So that's why we assume ks and we use this formula. Okay? So if he specifies that we have to use a different one, then we have to use a different one. Otherwise, we're going to use ks. So I'm just trying to show you guys if this is correct. I did the Excel of what we were doing earlier. And if we check for d, if d equals 4, yeah. So here we go. Yeah, tau, this is what we're supposed to get. This is the Excel formula. So we know we're getting it correct. So if we went for 4, this is what you would get. If you went for 2.5 for 2, this is what you would get. Now obviously these values we ignore because these values are greater than 31. So this is not what we're doing. Now this approach was done via what? We were assuming D. Another way of doing this is if we assume C. So if we assume C first, because we know it's 4 to 12 C, then these are our values. Now, we need to check whether our D outer is greater than 30. Now you'll see that these are only values that are greater than, less than 30, less than 25. Oh, not even less than 35. This is the only one that gives us less than 25. So this is a D outer. This is the only one that gives us less than 25. And the diameter of this is 2.25, we're assuming in this scenario. So anything above 4.4, you know it's not going to be correct. So there's that. Okay. So let's try another question. So let's try, for example, okay. So we're given another example here, and we're told to solve this. So let's go down, let's add another page. So over here, let me make this one smaller. Okay. So a mechanism is used for printing. Machinery consists of a tension spring assembled with a preload of 30 newtons. The wire diameter of the spring is 2 millimeter with a spring index of 6. The spring has 18 active coils. The spring wire is hard drawn and oil tempered, have the following properties. So design shear stress, modulus of, so this is tau, this is G. Determine the initial torsional stress, shear stress on the wire, the spring rate, which is, if you remember, its spring rate is just the stiffness. That's what it is. And force to cause this body to reach this yield strength. So how do we do this? We need to find the torsional stress. Now, torsional stress is, again, we can use any Ks, Kw. We can use shear stress here as well. So if we go with Kw, for example, if we go with, Ks, and this question, most likely he will tell you to use Kw. So if we use Kw, Kw is 4c minus 1 over 4c minus 4 plus 0.615 over c. Now if you remember what's Ks, Ks is just 1 plus 1 over 2c. So these are just values. These will just give you a number. It doesn't matter what K value you use. He will specify it. But for this sake, let's use Kw just to make it a bit different. Because in an exam, he will make it a bit different. So let's use Kw here. And you will get, 4c minus 1 over 4c minus 4 plus 0.615 over c. Now, why are we doing this? Because we want to work out the torsional stress, the shear stress in the wire. How do you do this? T torsional stress. Now how do you do this? This would be the initial stress. This would be Kw, right? And this would just be 8fc over pi d squared, right? How do you know this? If you go up again, look over here. So it's Ks over here, fc pi d squared. And this is exactly what we're doing here, fc pi d squared. So it doesn't change anything. Now, they've already told you certain things. Now let's go back to our given things. We should always write down what's given. Preload is 30, so our F is 30. Our small diameter is 2, small d. And they tell you C, which is d over d, is equal to 6. And n equals our capital N equals 18. And we also know that our tau max, our tau is 680 and G is that. Okay, which we already discussed. So the initial, we're trying to work out the initial torsional shear stress. So we can label this as T sub I. So how would this work? So Kw, so let's work this out first. So 4, C is 6, 4, 6 minus 4 minus 1 plus 0.615 over 6. Now, what would this look like in the calculator? So again, so 4 times 6 minus 1, 4 times 6 minus 4 plus 0.615 over 6, which is 1.2525. So this is 1.2525. Now I will do Ks as well, just to compare, right? Just to compare. So that will be 1 plus 1 over 2 times 6, which is 1.083 recurring. So 1.0833. Okay. We're going to use both of them, and we'll see where we end up with. So we'll try Ti. I'll do it in red maybe. I'll do it in red. So this will be Ti, but this will be for Ks. 8fc pi d squared. So let's try Ks first. So 1.083, right? 8, what's our f? F is 30, so 36 over pi times our d, which is 2 squared. Okay, we'll compare both of them, and we'll just change the values. So let's stick with this. So answer times 8 times 30 times 6 over pi times 2 squared. So we get, for this one, we get 124.14, right, MPa. Okay, now let's compare this to if we were to get another answer. So let's write 1.2525. We get a significantly higher initial torsional stress, shear stress, of 143.5 MPa. So 5.3, I guess. Okay. Now, why is this important? It's not really important to work out the spring rate, which is our constant, our stiffness, right? So because we know K is equal to what? K is equal to over here. So let me see if I can just copy this again. So let's bring this down here. Control V. All right. So K is just dg over 8c cubed n. Now this will be the same for both of them. So for if we use Ks or if we use Kw. So small d is 2, right? 2 times g is 80 times 10 to the power 3 or 1,000 over 8, what's c? C is 6, so 6 cubed times n is 18. So let's check what this will give us. And yeah, okay, let's check. So spring rate should be, let's check. So okay, so 2 times 80 times 10 to the power 3, shift 3. Then we have 8 times 6 cubed times 18. 5.144, and all this is repeated. So 5.144, and stiffness is Newton per millimeters. So this is our stiffness, and if we use Ks, this is our initial stress, this is our Kw if we use Kw. Now, we want to find out the force caused, so we're going to assume another force, let's call it F, let's say yield, Fy, or F yield strength, so Ys, I guess, yield strength. And we need to work out this yield strength that can counteract the tau being 680 megapascals. So how do you do this? Again, we already know tau is equal to what? It's either K, right? In this case, K, Ks, Kc, whatever you want to use. We'll do both of them, and we'll find out the separate cases. So we do T equals Kw 8f c over pi d squared. And then we'll do the other one, t equals ks 8f c pi d squared. Now, we know AT, we know that this is equal to, I'll do this in, say, green. So this will be 6 AT equals KW, which we said earlier, for KW is 1.2525. So 1.2525 times 8 times FYS times C is our 6, all over pi and times 2 squared. Now, this FYS would be, now this is a cool thing you can do in the calculator if you look, if you just do 6 AT alpha equal 1.2525 times 8 times alpha x, because we just want x, all for x, times 6 over pi times 2 squared. You do shift solve for x, and you get x as 142.13 newtons. So we get FY 142.13 newtons. So this is for FYS. And we're going to do the same thing for KS, if we use KS. So the only thing we're changing is our K value. So if you go back here, this will be 1.083333, and again shift solve, and we get 164.33 newtons. So 164.33 newtons. You'll see that using KW gives you a more conservative estimate, and the other one will give you a bit more larger estimate for the force. Now, the next question says design a helical spring. So let me bring this question out. So if we have this over here, so let's try this question over here. So turn 3.5, design a helical spring, and for a maximum load of 1,000 newtons for a deflection of 25 millimeters with a spring index of 5. The maximum permissible shear stress for a spring wire is 420 megapascals, and the modulus of rigidity is 84 kilonewton per millimeter squared. And they've told you to take the Wahl's factor, which is K. It's a bit cut out there, but this is just C minus 4. So what's given to you? We're given force equals 1,000 newtons. We're given deflection is 25 millimeters. We're given C is 5, which is also equal to capital D over small d. And the question on tau max is given as well, which is 420 megapascals. And G is given as 84 times 10 to the 3 Newton per millimeter squared. Okay, so we're given all this information, and we're told to use the Wahl's factor. So we already know what C is, so K will be 4 times 5 minus 1 over 4 times 5 minus 4 plus 0.615 over C. So let's work this out. So this would be, let's go here again. So I'm just going to write 20 minus 1 because I know what 4 times 5 is. And 20 minus 4 plus 0.615 over C. C is 5, so let me just change this to 5. So over 5. We get 1.3105. So 1.3105. This is our K, and we know that our tau max is equal to what? It's equal to K, in this case KW, right? Times 8FC over pi d squared, right? So our tau max is already given to us. We're trying to work out what? We're trying to work out the maximal shear stress is given to us. We're trying to work out the design. And design means what? You need everything. So work out everything. Work out everything. Okay? So that's what design means. You have to show all the quantities that you can figure out to show this. Okay. So with this, I can work out D with this formula. So first, let's rearrange for D because it's much easier that way. So that would be, so let's write, so tau max pi d squared equals kw 8fc. So d squared will be kw 8fc over tau max times pi. So d would be square root of all this, so kw 8fc over tau max, I'm just going to write tau m times pi. So this makes our life easier for ourselves, so well, I should have done d and then like this. Okay. So square root, answer times 8 times force is 1,000, times c, which is 5, over tau, which is 420, right? 420 times pi, and we get 6.303, so 6.30 millimeters. So this is one of our answers so far, right? But this is just d. We need the outer diameter. When we're looking at design, we need to look at the outer diameter as well. So which is d plus d. Now, we now know what d, small d is. We can find out that c is capital D over d. So capital D is c times d. So d would be, so let's try that. So this times by 5, 31.5, right? So we get 31, yeah. So we get 31, 31.5, let's say 5, 2. And then we add it to 6.3, so this would be 31.52 plus 6.30. So plus 6.30, 37.82. So 37.82 millimeters. This is our D outer, right? So yeah, okay. So with this, was it 5, right? That was 5, yeah. Okay. Yeah, okay. So the outer diameter is 37.82. Okay, so that's one thing we can add. So another thing we can add is, we can find out is the number of turns. We don't know the current active number of turns, but we do know that we have our deflection is 25 millimeters. Now if that's the case, what we can do is, if you remember, F equals K del X, so we can rewrite this. So F equals K, I'm just going to write del X. So we need to find what this is. So this is F over K. And if you remember, K is this insane formula over here. So I'm just going to write this over here. Okay. So this would be F over K. So dg, K is this. So I'm going to write 8fc cubed n over dg. Okay? That's what it simplifies down to. Now, what do you want? We want n. So n would be our deflection multiplied by dg over 8fc cubed. So we know it's 25 times our d, which we assumed is 6 point, if you look up again, 6.30. So 6.30 times by g. G is 84 times 10 to the power 3 kilo. And over 8. And our force, we're saying, is also, let's look at our force. Force is 1,000 as well. So they'll both cancel out. And c, we said, is 5, so 5 cubed. Let's look at the active number of turns. So if I go up again, okay, so equals, I try to use exact values, it helps in the calculations. So, I mean, it doesn't make a difference, to be honest, if you use, because it's already to like 2 significant figures, 3 significant figures, so it's fine. 84 times 10 to the power 3 over 8 times 1,000 times 5 cubed gives you 13.23 turns. Now, you can't have 13.23 turns. You can only, if you're more than 13, you're gonna have 14 active turns. So our n will be 14. You cannot have 13 and 0.23 of a turn. So yeah. Okay. Now, we're not told what type of ends did this does this what do you call it have. But we are told initially. Look, we're told for plane ends it's just n. For squared and ground ends we add 2. For squared ends we subtract 2, I think. No, we add 2 as well. We add 2 as well. And for plain ground ends we add 1. So if we were told which type of ends we're using, so this will just be for normal, right? So if we were told, for example, to work out the n for squared plus ground ends, then this would be n plus 2, which is 16 turns. Okay? Okay. All right, so that's it for this one. This is all the design specifications. Let's see if we can do another thing. So another example, we're told, so let's see if we can find this out. Okay, so example 23.6. All right. So we're told design close coil helical compression for a spring with a surface load of 3250 to 2750 newtons. The axial deflection is for spring load is 6 millimeters. Assume spring index of 5. The permissible shear stress tau and g is given. Neglect the effective stress concentration. So what does that mean? We're going to use I believe no K, right? No K will be used. Okay. But I think this type of question he won't give because most likely he will ask us to use K. So there's also this. So maybe this is not a good example of, for example, let's say, a question that can come. All right. Another question that can come is, for example, let's try another one. Let's see, probably. Okay, let's try this one. Let's try 23.9. Okay. So we're given the following information, and they also tell you to take Wall's factor in this example here. Obviously, we can use based on what's given to us over here. Oh, sorry. All right, cool. Okay. So we have a safety valve of 60 millimeter diameter, right? 60 millimeter diameter is to blow off at a pressure of 1.2 newton-meter per millimeter squared. It's held on a seat by a closed coiled helical spring. The maximum lift is 10 millimeter. Design a suitable compression spring of spring index 5, so that's C. Initial compression is 35 millimeters, so that's our delta. Our extension, a wide limited to 500 megapascals, so that's our tau. Modulus of rigidity is 80 kilonewton newton per millimeter squared. Calculate one diameter of the spring wire, a mean coil diameter, the number of active turns, and the pitch of the coil. So that's that. Now, how can we do this? So let's first look at what we're given, right? We need to work out the diameter of the spring wire because we're not told the diameter of the spring wire. What we are told is the safety valve is 60 millimeter diameter. So what we can say is that if we assume that D, right, is our diameter of the spring wire, right? This is our diameter of the spring wire. Okay. We also know the maximum load something can take is what? Is, F equals, or pressure equals force over area. The pressure equals force over area. So force would be pressure times area. We're given the pressure, and we're given this diameter. What we can do is we can find out the load of this initial valve, or this at the valve, right? So this would be pressure is 1.2, right? And our area is pi d squared over 4. So if we assume that the d is 60 millimeters, you'll get that it's 1.2 pi times 60 squared over 4. So let's check. So pi times 1.2 times 60 squared over 4. So we get 3393 newtons. So we get, okay. Now, to work out the so diameter of spring is obviously 60 millimeters, that's why. Now, the mean coil diameter, we don't know yet, right? So we're still working out the K and everything. We still don't know what D is right now at the moment. We're just assuming this is the spring. This is not the D that we're supposed to take, right? Okay. Now, to work out the maximum compression would be what? We have to work out that, look, if you look over here, that the initial lift is 10 millimeters, and then you have another, we have to provide 35 millimeters as well. So if you look at our max, that would be 10 plus 35. So we should get 45 millimeters max extension. Now, we also have the load of initial 3393, which keeps the valve on its seat by providing this 35 millimeter compression. Therefore, the maximum load on the spring when the valve is open is what? So it's basically, this is when you have 35 millimeters. So we divide this by 35, and we times by 45 to get the actual load. So what would this be? The actual would be 3393 or 35 times 45. If you want to visualize this, imagine you have 35 millimeter extension, which gives you corresponding value of 3393 newtons. You want to work out what you get for, what's this? You just cross multiply. If you call this x, so this would be 35x equals 3393 times 45. And then x will be 3393 times 45 over 35, which is what I've done here, which is the same thing. So let's check. So this answer over 35 times 45. Get 4362 newtons. Now we have our force that we want, and we need to work what? They also ask us to use Wall factor kW. Now, to work out D, we also know that tau max is 500. We also know from before is what? We also know what? We also know that C equals 5, which I C equals 5 over here. All right. So we know that for tau max, which is 500, this is equal to kW 8fc over pi d squared, right? Now we need to work out what d is. So all we have to do is d equals, well, I'm simplifying here because of time. So this would be kW 8fc over tau times pi, right? Now we haven't even worked out kW is kW will be 4 times c. C is 5, right? So 5 minus 1, 4, 5 minus 4 plus 0.615 over c. Now we did this earlier. If you look, we did this c earlier. This was 1.3105. So we're going to use the same one. 1.3105. So this will be equal to 1.3105 times 8. The force we're using is 4362 newtons times c, which is 5, over tau, which is 500 pi. Okay, so let's this in the calculator to get our actual diameter of the wire. We assume we're assuming that if d, so this is different. This is diameter of the safety valve. This is not the diameter of the wire. So please do not confuse that. So square root 1.3105 times 8 times 4362 times by 5 over 500 pi, and this gives us a value of 12.07 millimeters. This is the diameter of the spring wire. So that's part one. Now, how to work out the mean coil diameter? Now, when they're asking about mean coil diameter, they're asking about what? They're asking about capital D. Now, how do I work out capital D? So this is part two. Capital D is equal to what? We know that C is equal to D over small d. So D is just C times D. So that's just 5 times 12.07. So our capital D is equal to what? It's just this times 5. So times 5. 60, 60.3, so 60.3 millimeters. Okay, so that's what we have. Well, let's make it a 3.33 millimeters. Okay. Now we have to work out the number of active turns and the pitch of the coil. So number of active turns. Again, if you remember, our delta, or it was started with F equals K del X, and then we got del X, or delta, is equal to 8F C cubed N over GD. We want to work out what N is, so we're just going to rewrite this. So N equals GD over 8F C cubed. We know the initial deflection, or the total deflection, is 45, right? And G is 80 times 10 to the power of 3. And our diameter now we're going to use is what? 12.07. Now in reality, obviously, we're not going to use a diameter of 12.07. We're going to use what's given to us in tables. So we're not going to use this value in the real exam. Not a real exam, but in reality, we're not going to use these ones. If we're asked to use a different diameter, we're going to use the one that's just above this in the tables. Okay? So 8. Our force we know is 4,362. If we go up, we did over here 4,360 newtons over here. So this is 4,362 newtons. And we times by C, which is 5, and cube it. So let's check. So before we do anything, let's go back. Let's divide this by 5. So we have this answer. Let's shift store it at B. I want this answer as well. So let's this was this, so let's shift store this at A. So now I have both my values. So 45 times 80 times 10 cubed times alpha B over 8 times alpha A times by 5 to the power of 3. And this gives us an active turn of about 9.95, which is around 10, right? So this is 9.956, which is N equals 10 active turns. Now, if this diameter was a bit bigger, because if you look at the actual size of diameters, the actual leg size is 12.7. If we were to use 12.7, so instead of this, if I use 12.7, you'll notice it's 12.48, so this would give us an N of 11. So this is from tables. So if you use tables, we would get an N of 11, just so you know. Okay. Now, next one is the pitch of the coil, right? So the pitch of the coil, we can work out. Well, the pitch of the coil we weren't really taught how to do, so I don't think this will come. And yeah, okay. Anything else? Okay, so I think this is it for where springs and helical extension, sorry, compression, so springs. So yeah, good luck, and I'll see you next time.